तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking into the design of ROMs earlier. We will now have a look at the design of RAM, and this falls under VLSI category, deep into the VLSI category, in the sense that we may encounter much about 50,000 transistors. And once again here the requirement arises for a particular memory organization from the design application. Actually this application is also for DCT-Q, which we have seen earlier, and it requires dual RAM. It is not a dual port RAM, mind you, it is a dual RAM, in the sense we have two RAMs inside this black box to start with, and each of these RAMs will be storing the image information, and this information will be written through PCI bus. And prior to going to describing these signals, we will see what it really does. It, as I mentioned before, it has two RAMs. When you start with, you will be writing into one of the RAMs, and the other RAM will not be accessed. And once the first RAM is filled, the same image will be filled. I mean, different block of image will be filled into RAM 2, and when this happens, concurrently we will be reading from RAM 1, which was filled earlier, and then process DCT-Q from that block of image. That is, first block of image will be processed, while second block of image is being concurrently loaded into this RAM, and that is how the requirement arose here. And another special feature in this dual RAM is it's not really as it's special in the sense it is arising on account of the requirement for this DCT-Q evaluation. The feature is when we write into the RAM, we will be writing 8 bytes at a time. So that is 64 bits. We have also said that it is through PCI interface bus, assuming a 64 bit data bus here. This is for the PCI signal, and we will be writing 8 bytes at a time. And while after we have we need to write only 8 times, because what we need is only a block of image data, and which is 8 by 8 pixels. Each of these pixels will be just 1 byte if it is monochrome. If it is color, it will be a 3 byte. Right now it has been implemented for monochrome, and you can always duplicate this dual RAMs, triplicate rather, and in order to achieve color motion picture as well. And here as I mentioned before, we will be writing into one of the RAMs here, and in order to write what we need is a separate input here. It should be 8 byte in width, that is 64 bit, and this is the PCI compatible input bus through which we will be writing the actual data, image data. We have in bus arbitration logic earlier, we have precisely considered this particular application, and we have seen that video grabber is used, and on it goes over to the codec thereafter, and within the codec this is the design that is been housed, and when this is valid is indicated also. This is also we can derive it from the one of the PCI signals, and there are many more PCI signals. We are not considering all at this point of time. You can bunch all the other requirements into what is called a data invalid. So when this data is valid is being indicated here, and once again there are 8 bytes, and each of these bytes when it is valid will be indicated by BE signal, stands for byte enabled. This is also a PCI signal, and there are 8 bits totally, and whichever is made 0, either 0 or 1, so we can always invert the logic if you find any mistake. So I think I have assumed 1 here, maybe 0 is the right thing. So it all calls for just inversion in the logic later on. So to start with, suppose you make a particular B bit go high, then only that byte will be written into, and in real practice, being a 64 bit, all the 8 will be active simultaneously. That is the implication there, and so in order to write here, we need only 3 bit address for write address, and this corresponds to 8 such locations, and each location is 64 bit in width. So you have a question?
Wouldn't you have followed that 3 bit notation even for that byte enable also, instead of using 7 bits?
Let's say this is not my making, this is part of the PCI specification, so you can't help that, right? So here I am at liberty to do that, so I have made what you had expressed, and what you have written you can also read, and prior to reading we should know whether a particular RAM is in write mode or read mode. It will one particular RAM, out of there are 2 RAMs, say RAM 1 and RAM 2, out of these 2 only one RAM will be in write mode, the other will be in read mode. So and that is how we accomplish continuous stream of image being fed in. So processing is happening concurrently, and in order to distinguish this one, you have another control called R and W, N for negative, that is low, read low, and write is high. This is the nomenclature adapter here, and these are all the design, signals pertaining to the design, whereas DI, then PCI clock is also there. These things pertain to the all these 4 pertain to the PCI bus, and there is also a system clock for this, especially for evaluating DCTQ. So that clock is this here. So there are 2 clocks here, one is PCI clock, other is the system clock, and once you have written into a RAM, so what we will be doing, we will change this value so that the 2 RAMs interchange their roles. So what was written into will now be read, and you need a read address, and that's once again it is 8 locations read, that is what we are seeing here, and as I mentioned, there is a special access in this RAM which is quite different from the conventional. In fact, the whole design is totally unconventional, and that special feature is, as you write, you will be writing along the row. The organization is 8 into 64, so all along the row you will be writing into, but while reading you will have to read it vertically. That means to say, let us say there are location LOC 0 through 7. So we will be reading LOC 0 higher order bit, byte 63 through 56, and location 1 next same number of bits, and so on. So, what you write horizontally or row wise, you will be reading vertically, or so that is the requirement arising from the DCT algorithm the speaker has developed earlier for DCTQ, and which we will be considering later on. And with this background, I think we will be in a position to read go through the design. So, before this, let us look at the comments here. RAM 1 and RAM 2 are the dual RAMs, 8 into 64 bits each. If RAM 1 is in read only mode, then RAM 2 is automatically configured to the write only mode, and vice versa. This is what we have already seen. Write the RAM row wise and read the RAM column wise. So, here we have to include another sub module. We have seen earlier that how the hierarchical approach by a flow chart, there will be a top module, the module that you see here, which is called dual RAM, given an apt name, and this contains two RAMs. You have to access RAM 1 and RAM 2. So, this RAM will be in a different file as such, and that RAM must be included here. And we have also said that specialty here is row write and column access, and that is why I have labeled like this. So, it is basically a RAM. This implies only a single RAM, but this is invoked twice in this design, and thereby you make a dual RAM out of it. And we had to declare module name, then give apt name and list all the IOs here, and IOs are precisely what we have seen in the diagram above, and that is a clock, PCI clock, RNW, BE, read address, write address, and this is the data in and its valid signal, and this is the signal for out. So, out comes the column wise read data, and what we have listed here we have just tabulated here, and you can just have a look quickly. So, all these are inputs, and comment will make it self explanatory. PCI clock for inputting data, DI sets one RAM in only read only mode, RAM sorry, it is a write only mode, and the other RAM in read only mode, and this is data valid and this byte enabled. Then read write, you can even club like this if you wish, or you can make it separate, and input for the data here, and data out, and width is also mentioned here. We have a signal called switch bank, and this is nothing other than R and W inverted. As you can see in this statement, assign switch bank is inverted signal. So, why it is inverted I will explain a little while, and we have two outputs corresponding to the two RAMs. That is why we have nomenclature it as DO1 and DO2, and DO next, as we have used earlier, is the is to indicate the next value of DO, which is the register value which will be at the next clock positive clock edge after this DO next goes active, and DO is the output, and we had to declare all this as wire because they are all assigned statements, and this is basically it is in always block with a positive edge clock, and they are all basically registers, and so this particular control is to configure RAM 1 and RAM 2 for read or write mode respectively to start with. So, that is why we need here, and this will be more clear when we really go into the actual module. So, now we are in the dual RAM, this is the top design, and we are going to call sub module such as RAM RC, and this is what we are going to see later, and here we call this design twice, once for invoking RAM 1, and all the IOs are listed here, and this is precisely the same IOs that we have on dual RAM, namely clock, PCI clock, RNW, BE, read address, write address, everything is precisely same, and DI and DI invalid and final output, and except for the fact that we have a, 2 such RAMs invoked in this design, and otherwise this signal listing is precisely the same. So is the case for the RAM 2. So we invoke this RAM twice and thereby get 2 RAMs in this particular design, and how we blend this we will have a look. And here as I mentioned, switch bank was inverted R and W, and here for RAM 2 it is different here. This R and W control is the one which will configure it as read only or write. So now let us have a look as to what has been configured. So in this case what it says is, if R and W equal to 1, that is without any inversion we are straight away taking R and W here for RAM 1, and if R and W is 1, 1 stands for the write portion, and that means to say this RAM 1 is configured for write mode, and otherwise it will be read mode. For the time being let us stick on to one particular state, so as to know what the role of RAM 1 and RAM 2 are. So clearly RAM 1 is in write mode if R and W equal to 1. Let us see what will be the state of affairs for RAM 2 for R and W equal to 1. In this case it is an inversion of R and W, because switch bank is an inverted R and W, and if R and W is 1, automatically here the local R and W is actually 0. So that means it goes to read mode. So when the RAM 1 is in write mode, RAM 2 is automatically configured for the read mode, and vice versa, and that is how you can continuously fire the image into this dual RAM, and automatically this swapping will take place. This R and W will be automatically taken care in a controller which will be considering when we consider DCTQ design. That controller is not part of this dual RAM. And once again all the other signals are precisely the same, except for the fact that DO is nomenclature now. This DO2 refers to this top design, that is the dual RAM, and similarly for the RAM 1 it was nomenclature as DO1. So this distinguishes, that is why this has been declared as a wire, you could have seen here, DO1, DO2 are, and so I mentioned in one of the test benches way back, so how we call from top design lower submodules, and this is the first thing I think we have encountered, calling the submodule, and this is a separate file which we will be looking into shortly. So we see that if R and W equal to 1, RAM 2 is configured for read mode, otherwise write mode. It is exact reverse of the RAM 1 condition. And here what we do is we need to have we want to have pipeline stage, we want to register basically. So that we do only at always positive edge clock, and here the final output is DO, and the DO is derived from basically a DO next. This in turn is derived from either RAM 1 data output or RAM 2 data output, and that depends upon this R and W control. And the reason for one delay is being invoked here is to delay the actual R and W by 1 clock pulse, just to keep pace with this delay, because we are outputting at after clock edge. So in order to keep step with that, we are delaying that, otherwise the whole thing goes topsy-turvy. Just one error you make, the whole thing will become totally dead system. And in fact I landed up in such a trouble after a few days only I could discover that. So be on the lookout for such pitfalls, and is this clear to you? And so that is how you get D0 next at the final output, and this is what you want, either a RAM content from RAM 1 or RAM 2 content, that is for reading. While reading only this is valid here, and while writing it from the PCI bus it will be straight away written. When we go into the RAM details, the next file, that will become clear. So this top design is a very simple design here. It merely invokes 2 RAMs, and that is the end of the module there, and we will go into the RAM RC, this is another file, and this file is being called by dual RAM, that is what is indicated here. And RAM size is, as you know, 8 locations of width, 64 bits, and writing is done with row addressing, reading with column addressing. This also we have covered for dual RAM. Same thing applies for RAM RC. And once again the IO details are exactly the same as we have seen before, and the listing of the same. So now we have this special command called regmem. We have seen before that we can have RAM of size 64 bit and location 0 through 7, this being the highest order. So location 0, location 1 and so on, location 7. We have seen earlier in the ROM design. Same thing can also be used in RAM design, and only here the difference is it was read only there in ROM, and here it will be both read as well as write, and DO is the final output for the RAM. It is basically a register array of 8 into 64 bits. That is what the meaning of this statement. And we are using different, internal, as in ROM we are using lots of internal signals and of different bits. That is what we have listed here, and address is also either read address or write address. So a common address is invoked here, and width is 3 bits because we need to address only 8 locations. And as in ROM design we will have a location 0 through location 7 here, and they are all combinational circuits, therefore they have been declared as wire, and width obviously is 64 bits here. Then we also have signals derived from B7 through 0 we have seen earlier, that is different, and from this one, this is local, and there is more to this here, and they are all using assign statements, therefore they are declared as wire. And we also want to access column wise, we want to read column. So what we do is we have to have another signal for column, and that should be 64 bits, and that is in a block, always block, therefore it is declared as reg. Now let us see how to get address. We have seen before we have an address. This is nothing but a write address or read address of the RAM depending upon the R and W value. This is a mux implementation here. If R and W is 1, naturally write address is put into the address, otherwise read address, and get write address R and W equal to 1 or read address. That is the precisely what the comment is also saying. And we have another variable or signal rather called memory data, and this is nothing other than reading that regmem. So that memory is being read here with the address as ADDR, and this address would depend upon R and W. It could be a write address or read address, and fetch the memory content. That is what it says here. So here what we do is we fetch from independent locations. This is basically a location 0, therefore we put it as location 0. So assign statements have been used. This LOCs have been declared earlier as wire, and you have 8 locations 0 through 7, and they are nothing other than reading the actual content from memory straight away, and this is the address here. This is how you invoke the address. And we have an always block here, and this is for reading column wise. In fact, I should have put the other way, I should have started with the write, but it does not really matter. In Verilog all are concurrent statements, which way you put does not matter. Even now I can change it if I want to, it does not really matter. We will consider the reading first. So how a column is being read, we will have a look. So here we see that address is the one which gives the read address or write address, and you can use a case here in order to take actions depending upon what address is encountered. See, for example, here we are in the read only mode, because what we are going to do is we want to read the RAM column wise, and we should read this only when there is a change of any of these parameters here. That is why we have put an always loop, and mind you, this is still a combinational part only. Only when there is a positive edge clock it will become register sequential then. So in the first case what we do is we have seen location 0 is the first one with the MSB first, and LSB towards the end, because total is 8 bytes, that is 64 bits. So what we are going to do is we want to read column. So what we should do is go to the first location 0, read the topmost byte, and go to the location 1, that is vertically now, once again read the topmost byte and keep repeating this and concatenate all this here. So you have total of 8 into 8, location 0 through 7 is 8 and each is 8 bits. So all the 64 bits are intact, that is now row wise it is put, but actually it has been read column wise from the RAM. While writing it will be done row wise, which we will be seeing later. So this column gets this value for 0 0 address. If the address is 0 0, it has to get from location 0 onwards, but other locations are also involved because it is column wise reading, right. So that location 0 etc. have lost its meaning because of that. And here for address 1, what you need to do is exactly say all the locations are involved, but next byte is involved. You see 56 is the last one. So here it will start from 55 to 48, next 8 bits, and likewise for different addresses it will be different, and that is the reason why what was put row wise like this we read column wise. So you have a doubt?
So, doesn't it mean that you have to fill a complete table before you start reading it, isn't it?
Yeah, that is what I was saying. I should have mentioned the write first, then it would have shown you a clearer picture, but even now generality is not lost, or working functionality is also not lost. Shortly we will come to that. So for different addresses it is precisely the same thing, each time only the bytes keep changing. So to lower and lower order, finally when you strike say 1111 for address, that is the last one, you see that 7 through 0, which is the last, 63 to 0 was the one, and 7 last byte is being accessed. So this shows that we are accessing vertically, right. So what we had to see is, and default is also covered, you can either put a dummy statement or put some relevant statement there, and case ends here, and there was an always block actually, so begin and end here. And now we are going to see how to write. Prior to writing, this writing is going to happen through the PCI bus. Another PCI master such as a video grabber we have seen earlier will be writing into this core straight away, and this will be housed in the video codec that we have seen earlier example. So in this what we are going to do is, we have also seen in the block diagram at the start that BE7 through 0 being used as part of the PCI signal. This is a PCI signal straight away. Now we are going to generate from this almost similar looking name, but difference is, I mean this is a different thing from this, it implies that particular bit, right, and this is derived from ANDing R and W as well as DI invalid. R and W means it is equal to 1, 1 means it is in write mode. So whenever we are in write mode, only then this should be computed, and all of them are assign statements, therefore they have been declared as where earlier, and data in is the one we input the data, and corresponding valid signal is this one. So unless the signal is valid and unless it is in write mode, we should not write into that, and this is just a preparation, merely a byte enable only done in this fashion. In case you do not have higher order address from the PCI bus not decoded, you can decode that and include in this DI invalid. Enable write only if B is 7 equal to 1 and so on, that is the implication there, and if it is reverse, we may have to reverse the logic here. So we have only to put one inverter at the appropriate place. So any last minute changes can be very readily incorporated in Verilog that way, and same is the case for other B's here, and except that different byte enables are selected for that. So in order to write, we need to look into the positive edge of the PCI clock, and this PCI clock, as I mentioned, if it is PCI X bus it will be 100 megahertz, other PCI bus will be operating at 66 megahertz or 33 megahertz, and it can be 32 bit or 64 bit, and PCI X comes I think in 64 bits, and we have taken 64 bits, and we have seen bus arbiter giving over 250 megahertz operation, and these designs may not give that. So ultimately what counts is the overall speed when we come to the total design, and here in this particular writing what we do is write into RAM only if B is 7 equal to 1 and so on, otherwise do not disturb the RAM contents. So only now it will be valid, data is valid here and it is in write mode. And now what we how to write this, what we need is the address. So address is write address because R and W selects B is 7 only when it is in write mode. So evidently this address is a write address WA. So memory write address is going to be affected by these contents. What are the contents? We are going to write into this memory. So this is what we are trying to do. This is a PCI write, right? And in 8 clock pulses you would have written 64 bytes, whereas in DCTQ it will take 64 clock pulses to process. So that means writing time is very high, and this may have to be done from the video grabber, and that means you have lots of time for the video grabber, and because processing is going to take quite some time. And here what we do is what all we have here is we had to read the DI input. This is the PCI data bus, and we had to read the last higher order byte, and provided that a higher order BE7 is enabled, and if it is 1 then only this will be taken and assigned to memory whose address is pointed by this address. And if this is not satisfied, especially for read operation this won't be satisfied, then also this will be executed. So we have to take enough care for that. So what we do is simply write itself back to it. So this and this are precisely the same. So you write the very same data from this and write it back to the same byte. So that means you don't disturb the contents because it is in read mode. So it is taken care. So you had to be extremely careful while designing systems, and if you forget this one, naturally it will functioning will get affected. And so is the case for all the B byte enables till the very end, the last byte here, and the whole thing has been concatenated, and that's separated by commas. So the whole thing what you have here is 64 bits in totality. So once again here we need to output this, we are talking of the submodule RAM underscore RC, and the corresponding output is still a combinational output only, that is assigned from this column. This column we have seen earlier, we are reading column wise. How to read we have already seen. What we have read and put in column earlier, now we are going to output here to D0 next, and that is provided R and W is low. So low corresponds to this one. If it is write mode, naturally DO will be taken as DO next. So both it's scattering, the statement is scattering to both read as well as write, and read column wise from RAM only if R and W equal to 0, that is what I have said, otherwise do not disturb. And finally in the RAM underscore RC, at positive edge of clock we need to just push this D0 next into the actual output D0. This is the output that goes straight away as we have seen in the right in the block diagram which we started. And this is the test bench for dual RAM design, and as usual we will operate at 50 megahertz, and there is one more clock here. One of these is PCI clock, the other one is for the system clock. I forget which is what, we will have a look little later. So we need to include back connected files, and that is why we have put dual RAM underscore bano.b, and this is the test bench, and we are naming the module as such, and we need to examine only the output here. And in fact in waveform you can have a look at all other signals, and as far as test bench is concerned this is adequate, and width we are declaring, and we are listing all the IOs still need to be identified as reg for inputs, clock, PCI clock, R and W, they are all inputs and this B etc. read, write are all generated from this design. So you need to declare it as sorry, these are all sorry, they are all inputs still. B, there are inputs to this design, right. So all of them are inputs. So you need to declare as reg, and only one output is D naught, that has been declared there, and then we invoke the actual design and instantiate it here, and only one instantiation is used, and these are all the listing of the IOs that we have already seen. So as usual, we start initializing with clock, PCI clock to zeros and R and W in 0. So implying that what does it mean, which RAM is being accessed, you have to keep track. So it is, if it is 0, it means read mode here, and why should it be read mode, and data invalid is 1. So how can this be read mode? It appears to be contradictory, but let me remind you, it is not a dual port RAM, but it is dual RAM, it is different. So one RAM is in write mode, the other is in read mode. So which RAM, we can make a guess from this. So this is a control to put one RAM in write mode and to put the other RAM in read mode, that is what it means. So this clearly implies it is in read mode, and what will be affected, you have to see. And suppose you want to inhibit the write, what all you have to do is make it 0. If you want to test out other possibilities, you can do all this, and once again B you can change bit by bit, change 1 to 0 if byte write is to be inhibited. I have seen all this, and all of the functions are working, and you will have to run every time you make a change. And now the data comes here. Follow this carefully, and we will also have a look at the waveforms. And what we are going to do is, first we take one of the RAMs, let us say RAM 1, and RAM 1 is selected, and we are going to write into this RAM 1, right. And so here that means R and W equal to 0 has pointed to RAM 2, that means that is in read mode, right. So but very first block of image that you are going to write, there is I mean there is nothing available in the other RAM, so there is no point in reading that. So we do not have to read concurrently. So now what that is why we are merely writing the data there. For example, let us just remember this, 0 implies 60, I mean all the 64 bits here, instead of putting so many zeros I just confined to the 1. So you just remember there are zeros here, and next is it is easy for you to remember this data 1, 2, 3, 4 all in progression. So it you can F0 is the last one, and of course these data are all different. You may find little difficulty in reading the waveform, but let us do it slowly, then we will get it. And for each time there are 0 through 7 locations, that is what is mentioned here, and every time, because it is 50 megahertz operation, we have made 20 nanosecond we change, and staggering is done just to offset as we have seen before. And next time what we do is we write the next block. So now we will write it into RAM 2, and next block of different block of data is being written into, and note the difference here. So while we are writing, this is write for the RAM 2, we are also reading simultaneously from RAM 1, that is the implication there. So R and W is also changed here. Earlier it was 0, now after having written into the first block, we are going to write into second block, therefore we should not forget this R and W control, right. Actually in DCTQ there will be a controller which will do this automatically. So here we had to force it in the test bench. So you have a second group of data here. So from this point of time onwards, I mean you have both write as well as read, and then you have one more block here, probably there is one more block, yes, one more here, right. And in order to see all the blocks it will be a difficult thing. So we will see some representative, although I have all the waveforms, we will see some representative things. First let us go to the very first block what we have written. So this is the first block we have written, 0 0. Now remember while writing we are writing in this fashion row wise, that is horizontally, while reading we should read vertically. For example, this is the first byte 0 0, then 1 2 7e and so on it should go, and the next must be 0 0 3 4 and so on. So that is how we had to read, right. Let us see whether the waveform conforms to that. So first waveform is this is I will first read out before zooming. You have a PCI clock here, and that is this, and byte enabled, all of them are forced to FF there, that means it is all ones here, and you have a DIN valid asserted, so 1 here, and data is changing at every 20 nanoseconds, and here to start with it was 0 there, so that is precisely what has appeared here, and then we had written 1 2 3 4 up to F0, you remember. So that is the second one. Third was 7E 6A and so on, and like this you just remember, and we have some more here, that is a write address here, it is showing 0 here, 1 2 3 4, that is what I have forced in the test bench, and no read address here because we are writing the first block, and there is a system clock here, DC2Q operates or dual RAM operates on this clock, especially for the read mode, and we have a R&W control here, it is precisely 0 here, that is what we have done in the test bench, and D0 output will come only later on after having written all while reading the while writing the next block of data, then we will simultaneously read. So after 8 clock pulses or so plus pipelining, maybe 10 clock cycles only you may start getting it, and I will zoom this. So we have PCI clock B and so on, and this is the data in, you can see that 0 0 all this data, and time access here. So read address D0 output, and so write address, and some of this data if you want you can cross check maybe 1 or 2 here. 7E 6A and so on, right, 7631, 7E 6A 7631. So what you have written into it has gone into the RAM, that is what you see here, so we do not require this. So next is, so next set of data is 5B A5 and so on, let us have a look at that. So here here is what we get, 5B A5, then 4782, B 5 4782 and so on, right. So next block is being written into. Now let us have a look at the vertical reading, whether it is happening or not. So this is the first block, we should read 0 0 1 2 7E when we read. So let us have a look here. So I will zoom it later on. No, it's the second waveform also does not cover that. You can see the data there. So the third one is for the read. Now comes the first read here. So you can see here. So while this is happening, it is continuing to be written. Both are concurrent, as I mentioned, right? And now you see that read address has become active, and R and W has switched over from 0 to 1, and this is system clock, and you can see the very first data here, right here, and I will zoom it so that you can read. So you can see here, it's continuing to write here with the write address changing, so it is going to the next block writing, and concurrently you can see that R and W switching from 0 to 1 to write into the second RAM, and concurrently to read from the first RAM which has been filled prior to, and D0 output is this one, read address and this. So let us have a look here. So the output is here, let us check whether this data are conforming or not. Say for example, we had to read column wise. So, just remember some of this 0 0 1 2 7E 76, 0 0 1 2 7E 76, right. It is you can make sure. Then last one is 4731 and say 4731. So, in this fashion you can see next one will be 0 0 3 4 6A, last one is 8A. So, last one is 8A 0 0 3 4. So, it is reading column wise. So, we can see some more, probably we had 2 more to inspect, and it will be from different blocks. Only thing is we had to we will have difficulty in identifying the blocks, that is the difficulty. And here what you have here is last one I will read 0 0 F0 here, and you can see that 0 0 F0, that is what we have, B931 of the last one. So, it is B931 here, alright. So, are you able to see? So, here you can see that. So, we have seen 0 0 F0 B931, that is what it is, and one more waveform is precisely same, except that I think it is the very last block, it may have a look. So, let us just read the last one A519 etc. I will zoom this. So, this is the one last data. So, the last we had to go to the fag end of the blocks. So, that is somewhere here. Finally, what we are doing is only a reading. I will just explain this and answer your question. So, we are only reading. So, what we are reading is actually the data that we have written in the previous block, that is this one here. You can see this one 0 0 F0 82, and just remember that. Are we there? Is this one? Okay. F0, right? 0 0 here, there is one more there up, that is 0 0 0 F0 8276, 0 0 F0 8276, same, right. So, let us go, and what is happening here? Can you identify that? Maybe it has started writing the next block with some data. So by and large you can see that it is there clearly. Right.
How is this dual RAM different from my getting two separate RAM chips and making use of it?
Even there, how will you access vertically? Suppose the organization is 8 into 64 bits. Suppose you have used a conventional memory of 8 into 64, right? That will be only one address bus. When you give address, it will merely access row wise and give you the thing. All memories are designed in that fashion while reading. Whereas our requirement is while writing it should be horizontal, while reading it should be row wise. Right? You can imagine it as a matrix. So we are writing row wise, and I can just see. See, we are writing row wise in this order. So that means 64 bits are written straight away there. While reading, we need in the conventional memory. When you give a read, you will get only this row wise, right? Whereas our requirement is not row wise but vertically. This is because of the algorithm that I have developed for DCTQ which demands this application. So, I can't use the conventional memory, and that is the reason why I went for the specialized design for this, right. And let us have a look. Okay. So, we had 2 clocks, so they had to be taken care, and that finishes the test bench. Let us have a look at the simplified results here. This is the dual RAM design. So, clock, this is the system clock, it operates at 153 megahertz, and PCI clock is 133. So, you can safely go to PCI hopefully. Let us not jump to conclusion right now, because we need to see the back connected results, which will be got only in the Xilinx place and route, right. So, the device as usual have been the same, namely XCV 600 highest speed available there, and these are all the distribution of various buffers, etc. And now, as I mentioned here in FPGA, we have they have special RAMs available. 16:1 has been pressed into service, and 128 such RAMs have been used in this design. And we didn't specifically mention this, but automatically the tool has done it. And in terms of LUTs, it takes 934 LUTs, and it's only 6% of the 600,000 gate. And this RAM is over and above those LUTs. And place and route results, once again number of slices, etc. are given. This here also it reports same 128 RAMs. And finally, the total gate count is, it is quite a high value. We have been so far considering only 2000, 3000 gates right up to the ROM design, and now we have made a big leap. So, because of the complexity involved the design, and it takes around 40,000 gates. If you take, I am sure you would have gone through a digital course, you may be aware of the package 74 LS00, a NAND gate packed in a 14-pin DIP. And each of this, if you look into the transistor organization, you will see that 5 transistors have been used there. So, if you take 5 transistors per 2-input NAND gate, and you take that as a standard, so you will get enormous value there. So, 150,000 transistors, it will, I mean 40 into 200,000 transistors. So, what crosses 50,000 is categorized as a VLSI, and that is how it is. And the maximum frequency of operation is 99 megahertz. We are just falling from magical figure of 100 megahertz, right. Thank you.